Today we will learn about colligative properties. Our question of the day is, what is the reason for putting salt in water when boiling pasta? And what is the reason for putting salt on icy roads in winter? First, let's review a bit about dissolving. When solids are dissolved in water, they wiggle in between the water molecules to take up space. If you add heat to the solution and the water vapor is trying to push up and evaporate, the dissolved particles will get in the way. This means that the water has to have extra thermal energy in order to evaporate in the solution. This causes the boiling point to rise. We call this phenomenon boiling point elevation. Similarly, when heat is being removed from liquid water to cause it to freeze, the particles will try to line up by partial charge and lock in place in order to vibrate. The dissolved particles will once again get in the way of this happening. That means that the water has to remove extra energy to slow down enough to reach across the dissolved particles and freeze comfortably. The freezing point will drop in a phenomenon called freezing point depression. Now let's think about water trying to evaporate on its own. The water is pushing against the atmosphere. If you add dissolved particles to this, they will get in the way. Water will have a lower vapor pressure due to the increased difficulty in evaporation. We call this phenomenon vapor pressure depression. Remember, vapor pressure is the willingness to evaporate. That means the harder it is for a substance to evaporate, the lower its vapor pressure will be. These phenomena, among others, are called colligative properties. Colligative properties are based on the number of particles dissolved in a solvent. They cause the temperature range in which the liquid phase exists to expand to varying degrees. The more particles that are dissolved, the greater this effect. Before we continue on, let's review a little bit about ionic and covalent. Ionic compounds dissociate into ions. Each ion will count as a particle. Covalent compounds do not dissociate, and they count as one particle as well. Let's look at a visual representation of colligative properties. If you have water, we know that water freezes at 0 Celsius and boils at 100 degrees Celsius. However, if you add a solute, then the liquid phase will expand to a lower temperature for the freezing point and a higher temperature for the boiling point. In this case, a freezing point of -5 and a boiling point of 105. Now pause the video and try the show it you know questions. When you are done, you may resume and check your answers. Consider the following. What factor determines how much the vapor pressure, freezing point, and boiling point of a solution differ from those properties of pure solvent? That would be the number of particles dissolved in the liquid. Next, would a dilute or concentrated sodium fluoride solution have the higher boiling point? Explain. Well, concentrated solution would have the higher boiling point because it would have more dissolved particles than a dilute solution. These particles would attract the water molecules and keep them from boiling as easily, which would raise the boiling point. For 3 through 5, an equal number of moles of Ki and Mgi, which have the same number of molecules, are dissolved in equal volumes of water. Which solution will have the higher boiling point and why? Which will have the higher vapor pressure and why? And which will have the higher freezing point and why? Magnesium iodide will have the higher boiling point because it has 3 moles of particles dissolved, while Ki only has 2. More particles means you have a higher boiling point. Potassium iodide will have the higher vapor pressure because more particles makes it harder to evaporate. So Ki in solution would have a higher vapor pressure than Mgi2. Lastly, potassium iodide would have the higher freezing point because more particles makes it harder to freeze. So Ki in solution would have a higher freezing point than Mgi2. So notice how The boiling point, freezing point, and vapor pressure were all raised by adding more particles. Let's practice determining the number of moles of particles in solution per mole of solute dissolved. For number 6, NaCl is a ionic compound made up of a sodium and a chlorine, or 2 particles. K2S is also ionic, and it's made up of 2 potassiums and a sulfur, or 3 particles. Now, C6H12O6 is covalent, so it's going to stay together. It's not going to dissolve and break apart. Now, CH4 is also covalent, so it's going to be a single particle as well. NH4Cl is a polyatomic, so NH4 is going to be one particle and Cl is going to be the other, so you have 2 particles. Now, BaCO3 is also made up of a polyatomic and it's ionic, so normally you would think it would be 2 particles. However, BaCO3 is insoluble, so it's actually going to be 0 particles. It's not going to dissolve. H2S breaks up into 2 hydrogens and a sulfur, or 3 particles. Potassium acetate is an ionic compound that breaks up into potassium and acetate, so 2 particles. AgCl is also an ionic compound. However, AgCl is insoluble, so it's actually going to have 0 particles. It's not going to dissolve. MgOH2, or magnesium hydroxide, is also insoluble in water. Therefore, it will not dissolve. BaOH2 has 1 barium and 2 hydroxide ions, which are polyatomic ions, and so it has a total of 3 particles that it's going to break into. Sodium carbonate has 2 sodium ions and 1 carbonate polyatomic ion for a total of 3 moles of particles per mole of solute dissolved. And Na-NO3 has a sodium and a nitrate, so 2 particles. AlCl3 has 1 aluminum and 3 chlorines, or 4 particles, and KBr has 1 potassium and 1 bromine, or 2 particles. So in conclusion, if you have a covalent compound, it will stay together in a single particle. However, if you have an ionic that is soluble in water, it will break apart into its ions, and each ion will be a separate particle. If it is insoluble in water, then you will not have any particles because it will not dissolve.